Transducers exist to measure many different physical properties. A transducer converts that physical property into an electric voltage or current. And we're going to look at just a few of the basic technologies for transducers, for some transducers. Here we have a capacitive transducer, and this is used to measure displacement. You can see the capacitance C changes as the position of the two plates change. Capacitance is given by this constant. This value is if you're using inches for your units of length. Epsilon, which is the dielectric constant of the material in between the plates, and then A over D. A is the overlapping area, so that would be the area of the projection of one plate onto the other, and D is the perpendicular distance between the plates. So this can measure displacement in two different directions. You could move the plates in the direction of their parallel to the planes, in which case the overlapping area would change, or you could move it perpendicular to the planes, in which case D would change. And the sensitivity of the transducer will be different, so the capacitance will change at a different rate depending on which direction you're moving the plates. And you might also have some geometry concerns that would dictate which way you want to move the plates. A capacitive transducer is often used for measuring liquid levels. You can see here the two plates, and the dielectric constant of the liquid is going to be different from air. So as the liquid level changes, the capacitance of the transducer is going to change. These are typically coupled to a charge amplifier to output a voltage signal. This transducer generates a small voltage signal natively, and it's based on the piezoelectric effect, where if we have this crystal and we apply a pressure to it, it's going to generate some voltage. And that voltage is proportional to the thickness of the crystal and the amount of pressure applied. G is a constant that depends on the material. Piezoelectric transducers are often used to measure pressure in high frequency applications. They're used as accelerometers, where we tie a known mass, a mass of known value to the crystal and then measure the force required to accelerate it. And piezoelectric transducers can also be used as force sensors. A Hall effect transducer can be used to measure a magnetic field, and it's based on the property that a plate with a current passing through it, I, when exposed to a magnetic field B, will have an electric potential EH generated in a direction perpendicular to both I and B. And the magnitude of that electric potential is proportional to the current and the magnetic field, and inversely proportional to the thickness. And K sub H is a property of the material. This voltage is small, in the hundreds of microvolts, so it requires amplification. Hall effect transducers are more commonly used, though, to measure position. The transducer will be combined with an integrated circuit so that the output is not proportional to the field, but it's just off or on, depending on whether or not a magnet is close to the sensor or not. Here is an illustration. We have a rotating shaft with two magnets on it, and then the Hall sensor close to the shaft. Whenever the magnets are adjacent to the sensor, the output voltage will be high, and when they're not next to the sensor, the output voltage will be low. So the transducer would give, the Hall transducer would give an analog voltage, continuously variable relative to the magnetic field, but a Hall switch, a Hall sensor, typically just has the off or on, so it would be a square wave output in this example. Hall sensors can also be used to measure the position of a pneumatic cylinder or hydraulic cylinder. So here on the side of the cylinder you have the sensors. Whenever the cylinder is retracted, sensor 2 would have a high voltage and sensor 3 would have low voltage, and when the cylinder is fully extended, those voltages would be inverted. The final transducer here is an optical encoder, and this can be used to measure either angular or translational displacement. In the picture here we have a shaft encoder, so this measures rotation. From the end it looks like this. You have a disc with cutouts in it, and from the side you see that perpendicular to that disc there's a light shining. So here's the shaft of the disc, and here's the disc, and there's a light source. And as the shaft turns, the photodetector will get alternating signals of light and dark. And that will generate a voltage, a square wave voltage, which is typically amplified. And the shaft encoder signal can either be fed to a counter to measure the change in position, or if you want to get velocity, you can measure the frequency of those pulses, and that'll give you velocity. This is the simplest geometry for a shaft optical encoder. Changes can be made where you can read direction also, in addition to just displacement, or in addition to just pulses, you can read the direction that the shaft is going. And more complicated geometry can even yield an absolute position for the shaft encoder instead of just relative to some starting value. And here is an example of a commercial encoder. You can see the disc and then the light source and sensor.